To map the infinite dimensions of a Hilbert space, or to calculate quantum states, you need a highly specific mathematical coordinate system, the orthonormal set. The namesake of these spaces, David Hilbert, pioneered this framework. Before we build an orthonormal set, we rely on three prerequisites. First, we need an inner product space to measure angles and lengths. Second, we need orthogonality, meaning our vectors intersect strictly at 90 degrees. And third, we need a Hilbert space, a complete inner product space where these vectors can stretch into infinite dimensions without the math breaking down. If vectors cross at arbitrary angles, measuring one against another requires calculating overlapping projections. They cast mathematical shadows on each other, complicating every calculation. But when vectors are strictly orthogonal, snapping to exactly 90 degrees, that interference drops to zero. They become completely independent axes. Zero interference is only half the requirement. To measure anything consistently, we need a standardized unit of scale. We do this through normalization, scaling every vector so its length is exactly 1. Together, these unit vectors form a perfect geometric unit square at the origin. By combining the zero interference of orthogonal angles with the uniform scale of normalized lengths, we create an error-free measuring stick. This framework allows us to navigate and map any vector space accurately. We can express these geometric rules algebraically. This equation shows the orthogonal condition. The inner product of vector x and vector y equals 0 when x and y are different. To make it orthonormal, we add a second condition. The inner product of vector x with itself must equal 1. Mathematicians combine these two rules using the Kronecker delta notation. The most familiar example of an orthogonal set is the standard basis for three-dimensional space. The x, y, and z axes, often written as E1, E2, and E3, are all perpendicular to each other, and each has a length of exactly 1. The rules governing those three axes apply identically if we scale up to infinite dimensions, such as in little L2 space. Instead of three coordinates, we use an infinite sequence, where a single 1 occupies the nth position and all other terms are 0. The perpendicular geometry holds up perfectly, no matter how many axes we add. This chart shows the sine and cosine waveforms plotted over the interval 0 to 2 pi. If we calculate their inner product using an integral, the positive and negative overlapping areas cancel out entirely. The integral evaluates to 0, proving these continuous waveforms are orthogonal. Because the geometry of these sets is defined strictly by the algebraic rules of the inner product, we can manipulate complex continuous waveforms using the exact same math we use for simple three-dimensional arrows. According to Lemma 3.4-2 in Kreyszig, every orthonormal set is strictly linearly independent. This means no vector in the set can be constructed by combining the others. To prove this, we set a linear combination of our orthonormal vectors equal to 0, and then multiply both sides by a specific vector, ek, to take the inner product. Because all the vectors are orthogonal, their inner products equal 0, wiping out every term in the sequence except the one containing ek. Since the inner product of ek with itself is 1, we are left with the coefficient alpha k equals 0. If all coefficients must be 0, the vectors are linearly independent. So, if you have a massive linear combination of vectors, how do you isolate just one specific coefficient without grinding through a huge matrix calculation? You apply the exact same trick. By taking the inner product of the total vector, x, against your target basis vector, you instantly collapse all the orthogonal terms to 0. This isolates your desired coefficient. In functional analysis, these isolated values are known as generalized Fourier coefficients. We can sum the squares of these Fourier coefficients, which leads us to Theorem 3.4-6, Bessel's Inequality. This theorem states that the sum of the squared coefficients is less than or equal to the squared norm of the original vector x. Think of a three-dimensional vector casting a two-dimensional shadow. The shadow's squared length on the flat plane will be strictly less than the length of the actual vector. The reason Bessel's formula is an inequality is that your orthonormal sequence might not span the entire space. Unless your axis system is complete, your projected measurements will always be missing some of the vector's true length. Now we know how useful orthonormal sets are, but we rarely find them naturally in the wild. If you are given a set of messy, non-orthogonal vectors, you need a systematic algorithm to force them into a clean, uniform grid. That algorithm is the Gram-Schmidt process, which we will cover in the next section. Before we move on, let's review the 4 rules we established today. We defined orthogonality as a zero inner product, and orthonormality as adding a length of 1. We learned how to find generalized Fourier coefficients by taking the inner product against a basis vector, and we mapped the limits of those projections using Bessel's inequality. By treating infinite sequences and continuous functions like standard geometric arrows, these 4 rules give us the math required to process everything from Fourier analysis to quantum mechanics. If this step-by-step breakdown helped you parse your textbook, please like the video and subscribe to the channel. We are breaking down theorems from Kreyszig, Rudin, and more, so leave a comment below letting us know which proof you want to see next.